Hi, Mr. Bennett here. Today we're just going to have a look at an example of a question out of a test to do with low orbiting satellites, and we'll also do one with a geostationary satellite as well. So for this question here, it's just got some information about a satellite being launched and then moving in a circular orbit around the Earth. Okay, now key information when you start looking at it is something like this. Alright, so you need to be able to highlight that, okay, and then the Earth, well, that's the mass of the Earth, and that's the mean radius of the Earth. Alright, so what's actually happening is we're looking at a low orbiting satellite at a certain height, and we have to better calculate the speed. That's what we're trying to calculate over there. Alright, so thinking about what we do have, we obviously have enough information to work out the mean radius. So the radius of the satellite's orbit is the radius of the Earth plus its height. Alright, so if you add those two things together, 6.38 by 10 to the 6th plus 8.7 by 10 to the 5, then you get the radius. Alright, so the radius is going to be equal to that. So you go to your calculator. Alright, so 6.38. Now using your power button to the power of 6. Right, add 8.7 to the power of 5, and then that will tell us what our answer is. So that's 7.2 by 10 to the 6. 7.25. So that's equal to 7.25 by 10 to the 6th meters. Now you've got to make sure you're using SI units here. It makes it a lot easier. Alright, so I'm trying to find a formula that relates radius. Obviously we've got gravity, that's a constant. We've got the mass of the Earth and velocity. Now that's obviously our original formula, so we know that V is equal to the square root of G, mass of the Earth, and the radius. Alright, so for this particular question, it's just a straight substitution to there. Right, we know that's going to be, looking at your formula sheet, 6.63 by 10 to the minus 11. Mass of the Earth given to us. You will always be given that. You won't be expected to actually remember that. 10 to the 24 kilograms. And then the radius of the Earth, which now that's a really important concept, that it's the radius from the centre of the Earth through the satellite, so you always got to count for the radius of the Earth in there. So therefore that's going to be 7.25 by 10 to the 6. Okay, so you've got to go and put that into your calculator. So when you're doing that, it's just straight into your calculator using the square root. Alright, so 6.63 to the power of minus 11 times that by the Earth 5.97 to the power of 24, and then divide that by the radius, which is the answer from the previous question. So that would make that easy for us. And so that gives you a orbit speed of 7,388.8 meters per second. Right, so that's equal to 7,388.8 meters per second. Alright, so this is a question I've asked in the previous test. The second part of that question is to explain two benefits of using low orbiting polar satellites compared to a geostationary satellite for forecasting weather. So what are sort of things that we have to, this is the key thing here, have to explain, but we have to explain two benefits of using that. So there's more than obviously one answer for that, so let's have a look at this particular solution that I've written up here for you. So since the low orbiting satellite sweeps over a strip of the Earth each time they orbit the Earth, they can take an image that can be put together that is showing what's happening with the weather information every couple of hours. Right, so that's the sweeping nature compared to the geostationary satellite, which is just sitting over. And I think the second benefit is because they're low orbiting, you get very high resolution pictures where you're not going to get the same sort of resolution from a geostationary satellite. So that's just an example of how you might answer that question. Alright, let's go back to our thing and let's have a look at a question that you might be asked. Something like how high the height of a geostationary satellite. I've seen this one before in a test or an exam. Alright, so that's basically all the information you get given. Obviously you've got all your constant values. So the first thing you have to understand is what is the period, the time taken. So we know the period's 24 hours, okay, which we then have to convert to seconds. So it's times by 60 to minutes, times by 60 to get that to seconds. So if we go to a calculator, 24 times 60 times 60, and that's going to give us our answer 86,400. Right, you'll probably get used to actually knowing that value. 86,400 seconds. Right, what else do we know? We know G is 6.63. Actually, I'll just double check that because I don't know if that's the right value. Okay, 6.673 by 10 to the minus 11. That's on your formula sheet. We know the mass of the Earth is equal to 5.97 by 10 to the 24 kilograms. So the key thing is we know that our Earth's sitting here and this thing's taking one revolution around the Earth in 24-hour period. Okay, and we're trying to work out what the height is of this particular satellite, what H is. Alright, so the formulas that we do know what? Well, we know that V is equal to, we used this one before, GME all over the radius. Now, we need something connecting the period in there, don't we? Alright, so from that we could have gone V squared is equal to GME over the radius, and then we know that from there we know that V squared is equal to 4 pi squared R squared all over T squared. That's equal to GME all over R. And so therefore, if we're trying to find something with a period in there, and we're looking at radius, we're looking for the height, we can say that R cubed is equal to GME all over 4 pi squared, and that's the T. So therefore the radius is equal to the cube root of all of that. So thinking about what we actually do know, we know the period and we know all of those other things. So now we can actually work that out. So that would mean that we're looking at the cube root of 6.673 by 10 to the minus 11 times by the Earth, mass of the Earth, which is 5.79 by 10 to the 24. So it's really important you always show your substitution in the formula. T squared is going to be 8,640 squared, and then that's all going to be over 4 pi squared. Okay, so this is where you go to your calculator. We're going to do cube root. Is there a cube root button? I'm just trying to think. Again on here, oh yeah, there is two. Alright, so if you go to your math, right, there's, sorry, if you just go to your math button, number 4 is a cube root. Alright, so that's the easiest way to do that. So we've got mass of the Earth, G, 6.673 to the power of minus 11 times that by 5.97 to the power of 24. Then we times that by 86,400, and we've got to square that, and then we have to divide that by, you probably should put this in brackets, 4 square that. Okay, and then enter, and that will give us our height. So that there is 42,000. Okay, whatever that height is. Okay, 42,000 something kilometres, 42 million. What we have to do is have to take away the mean radius of the Earth. Okay, so if we take the mean radius of the Earth, which is 6.38 to the power of 6, right, and then that will actually give us our height. Okay, so what you get here is 3.585 by 10 to the power of 7 metres, and so therefore when you start looking at that, it's 3585 and then 4 zeros. Right, so that there is 35 million metres. So let's convert it commas. 35850 kilometres. Alright, so therefore you've got about 35,000 kilometres is the height of the Earth. Now the key thing here is when you get your answer for your radius is equal to the radius of the Earth plus the height. So therefore the height has to be equal to the radius, take the radius of the Earth. Okay, what we're doing there. Okay, so that's a really, really good question. Alright, and if you see what I've done over here is, you know, I don't actually remember this formula here. I don't actually write it down on my formula sheet or whatever. I actually learn how to derive that, how to actually sort of change it from that form into this form here. If I wanted to solve for period, then I'd rearrange that differently, and I would say T is equal to 4 pi squared all over G mass of the Earth, and then that would be R cubed, and then I'd take the square root of all that. So it's just a really, once you're in this, to this particular form here, it should be a really easy, you know, sort of manipulation so you can actually get the right answer.